I would like to thank Daryl and Bruce for organizing this wonderful conference and have opportunity to present this kind of almost finished project with my students. Yeah, as Bruce mentioned, there's no LM like used in the project. So hopefully this gets something maybe not quite the same to the other talks. But I would mention that this project would actually utilize two important building block in the LM, actually the transformer. Okay, the one is of course neural network, the other is so-called attention mechanism. These are the most, I think, the why the transformer is so successful in building the large language models. So we're going to utilize this to a component in doing the causal inference like task. So the fundamental goal is try to weaken some traditional assumption in the causal inference. Okay. Okay, so typically in a lot of sociology and political science and other domain areas, so people are wondering what's the so-called causal relation, okay, between two, one behavior and another outcome, okay. And so this is common. So for example, in political science, people care about if we have this campaign advertisement distributed into the population, and how that will change the vote proportion, okay, yes and no. And so in this case, we basically treated the behavior or the intervention accepted as so-called treatment. Okay, this is the TI here. Okay, and also we care about some downstream outcome, in this case the vote. So this is some behavior, some outcome will change based on the treatment. Okay, so another example if we provide this job training support in a community, whether this one will improve the final employment rate, okay, for this workers, and also in the school, if you provide the tutorial support, whether this will improve students' GPA. So this is all kind of causal inference problem. We want to ask whether after remove all these confounders, we still have this direct relation between the treatment and outcome. Okay? And the problem become more complicated when you have this kind of network among this population. But this network structure is quite often in social media like public health, economic, and other area. And this existence of this network, we actually introduce this intervention across the individuals. Okay, so if one student receive some tutoring support, and this will actually not only improve the student's own GPA, and it actually may have some positive effect on his or her friend's GPA. So this is kind of intervention because of the relation, okay, among these different individuals. So if we try to kind of quantify this kind of intervention, we're going to use the notation here. So yi, this basically stands for the outcome, okay, we observe at the i's individual. So the TI is the treatment, as we mentioned before, okay, some behavior or the intervention you received. So the problem can be formulated like this. So this yi, it not only depends on the TI, okay, the treatment on this own individual, it also depends on the treatment received by others individual on the network. Okay, so if you really want to have a math formula, so basically this yi going to be the function and the TI its own treatment and other treatment. Okay, T negative I. So this a T negative I basically is a vector summarize all the other treatments in other nodes or individuals on the population. Okay. And this will actually have a problem, okay, compared with the classic causal inference theorem. Okay, so because in the classic causal inference problem, basically we do not allow this intervention among the outcome and treatment. Okay. But why we need to care about this interference or intervention? Okay, so this not only just bring a new challenge when you try to estimate causal problem, itself has value. Okay, so in a lot of situations we want to quantify the degree and whether there is whether we have this intervention or interference among the individuals. So this is actually called spillover effect, or sometimes called peer effect. So you have different terminology in different like domain, but basically they point out to the same thing. Okay. So we can actually formulate the treatment, the causal inference problem when there is intervention among the individuals. Okay. So the first quantity we care about, of course, this is called average treatment effect, ATE. Okay. So basically, you just like calculate the difference between outcome on the two counterfactual facts. The first situation is that if you assign the treatment to all the individuals, all the nodes on the network, what's the value of the outcome would be? And we compare that with the other situation when no one gonna receive the treatment, okay, on the network. So we calculated this difference, and we average this difference across all the nodes, all the populations. So this is called average treatment effect. Okay. So in this talk, for simplicity, let's just assume we consider binary treatment. Okay, either you take the some like treatment, or you do not take the treatment. Okay, and the point is that we can further decompose the total treatment effect into two like different quantity. The first one is called the average direct effect. So you can see basically in the direct effect, we just control the treatment on other individuals. Okay, we set them at 0. We only change the treatment assignment on this own individual. Okay, so the difference in the outcome only come from whether the own individual take the treatment or not. And similarly, we can define this average spillover effect. Okay. So meaning that we just control the treatment for this own individual, but we just change the treatment on its neighbors. Okay. And this will also can cause the difference in the final outcome. So the average treatment effect can be decomposed as a summation between this like average direct effect and average spillover effect. Okay. So far, this is not very new because statistician or like economic, they already studied to quantify this so-called spillover effect, okay, or causal effect under the intervention. Okay. But actually, you can see this, if we just directly try to quantify the estimand like this will have a lot of serious like challenges. Okay. The first one, okay, is that typically we only have one observation on a single network. A lot of situations we don't have the luxury. We have the repeat measurement over the same population repeatedly. Okay, we only have one time observation. Okay. So everyone only measured once. Okay. And also this like a T negative I, as we mentioned, this can be a very high dimensional vector. So basically it's as large as the size of the network. So if you just directly try to quantify the estimate like this, it can cause a lot of problem. Okay. And so one clever way, so people come up with, is to introducing a so-called exposure mapping. Okay. So this is actually just a summarize function. Okay, it's just like a summarize, like how many treated neighbors. Okay, in one individual. For example, let's say the individual I. Okay, we just measure how many treated neighbors like close to this individual I. Okay, so in other words, we summarize this like high dimensional vector into one numerical value. Okay, so this can significantly reduce the difficulty when we try to estimate this causal quantity. Okay. So eventually you can see now we can reformulate this outcome model. So originally this like outcome depends on like a high dimensional vector, but now this outcome only depends on two real values, Ti, the individual I's own treatment, and the summary, this exposure mapping, okay, capture the treatment assignment around its neighbor. And we can similarly define the spillover effect as the contrast between the two different values of this like exposure mapping. So this is actually the summarize of people already done before. And you may wonder how to choose this exposure mapping. Okay, so this is the key problem. So on the left side, I just summarized like 4 common choice in the literature, and people how to set up this exposure mapping. Of course, the first one, the simplest one as mentioned, this is just to measure like how many treated neighbors you have, okay? So this like NY1, this just like is notation, okay? Just like indicate that we collect all the direct connected neighbors of the individual I, okay? Of course, you can relate this like direct connected individuals to indirect connected like neighbors to the individual I, okay? You can relate this easily. And similarly, you can average the treated number of treated neighbors, okay, by divided by the degree, or you can like set up a threshold. So this third like type of choice typically used in the public health study, okay, like when you try to study the spillover effect of vaccine, you can assume there's a cutoff if the proportion of like in the population taking the vaccine exceeds a threshold, then there's some like a effect, okay? And of course, you have this like weighted combination of the treatment assignments around this neighborhood, okay? So the common limitation is that people need to assume that this exposure mapping is basically known and homogeneous, okay? Homogeneous means that, so this mapping doesn't change, okay, across the different individuals. Everyone shares the same type of exposure mapping. Okay? And also we need to specify this exposure mapping even before we study the problem. Okay? Basically, you need to assume that this exposure mapping reflects the true intervention pattern. And in practice, we know that this is definitely not true always. Okay? The exposure mapping can be very heterogeneous. So meaning that you can imagine that how people get affected by others definitely depends on its own some like features. Okay, you can imagine that if one has a very strong immune system, so even like all his friends like get some like virus, and he or she may be still immune to that like disease, right? So this motivates us to consider about introducing the individual's heterogeneity, which is actually captured by this Xi into this exposure mapping. So this Xi is basically the collected individual information, like demographic information, or it's like own like individuals like message, okay? And so we really want to estimate, okay, the causal effect, the potential outcome, okay, of individual I, like, and we study how this outcome can change if like we looking at different individuals with different like covariant information Xi. Okay. So this is kind of the motivation. So you can see this like figures on the left side, okay? Of course, this is just a very abstract example. So you can consider we have like ego node I, okay? We just want to measure how this I, individual I, will affected by its 6 neighbors, okay? So the first 3 neighbors, J1, T2, J3, they take the treatment, and they can definitely going to have the spillover effect, okay, to this I. And you can see, let's suppose the Xi has some like features we denote as positive, okay? And the J1 also have similar like features, also it's plus. In other words, they're kind of similar to each other, okay, in terms of their characteristic or features. And so that in this case, we can imagine that if the J1 take the treatment, this will have positive spillover effect towards the I. And if you can look at another situation like a J3, so the features of J3 is actually opposite to the features of I. So one is positive, the other is negative. So if the J3 take the treatment, it can have negative spillover effect, okay, to the individual I. And you can also like try to consider more general situation when the Xi is not just a signal, it can be a very high dimensional numerical vector. So the degree of spillover is also going to change, okay? And this can be useful especially when we study the so-called assigned relation network. Okay, people are not always friends. Okay, people can be enemy. So if you enemy take some behavior, this will actually downside specific like outcome. Okay. And also, by introducing this heterogeneity in the spillover effect, we can try to capture the most influential neighbors for an individual. Okay, you have a lot of friends, but not all of them have the equal ability to affect your behavior. Some of them may be closer to you, maybe more similar to you guys, can have a stronger spillover effect. Okay, so motivated by this idea, we're introducing this called heterogeneous like exposure mapping. And so this still look a little bit like a weighted combination of your neighbor's treatment assignment. Okay, the TJ is the treatment assignment. But this tau ij, okay, this is the weight. And actually, we're going to estimate this weight from the data. This weight depends on the individual's covariance and the network topology structure. Okay, and that's why this is more like a general than the previous method. And I want just like have several assumptions, because now we try to estimate this causal estimand from observational data. Okay, we do not have the random trial study here, so we do need several assumptions. But the most important one is let's just assume that the individual's outcome only depends on its local information. Okay, so this is kind of reasonable assumption. Okay, you will be affected by everyone on the same network. You only will be affected by someone who close to you, okay, on the network. So the others are just like standard assumption. And so in this, like another important assumption is called additive interference assumption. So basically, we can decompose the effect into several parts. Okay, so this is the outcome of individual I. So first, it depends on whether this individual take the treatment or not. So this is Ti. So this is basically the direct effect. And the direct effect can also depends on its own features. Okay. So in other words, if we assign the individual's treatment like as 1, oh sorry, this is a typo, this should be 0. So this contrast should be the direct effect. And also the outcome depends on the pairwise spillover between a neighborhood J with the individual I. Okay. And this like a difference in the spillover here also depends on the covariance, okay, on the neighbors and the individual I. As we mentioned, we can estimate this like tau I, tau ij, this like so-called interference coefficient based on data. Okay. And the first like result is that, so based on this setup, eventually we can like translate this any causal effect you want to estimate as a basically linear combination of this interference coefficient. Okay, and if you actually organize this like interference coefficient together, this actually can be treated as a matrix. Okay, so all the diagonal elements, this is direct effect, and all the off-diagonal elements, this is basically the pairwise spillover effect between a node I and one of its neighbors. Okay. And due to time limit, I think we can skip the estimation part directly into the modeling part, okay, as we mentioned. So we can, as we mentioned, we can estimate this tau I and tau ij, this direct effect and the spillover effect based on the model. So when we try to estimate these like models, and there's some like challenging because we only have observational data, and this data are highly correlated due to the network homomorphy. So in other words, this mu I0, this is the baseline level of outcome under the existence of network homomorphy. So this mu I0 will be basically entangled with the tau I and tau ij. Okay, the point is that we need to remove the bias from tau 0 to estimate this tau I and tau ij. And there's some framework to doing that. So eventually, yeah, I think just directly jump to the point, as I mentioned. So basically, we're going to use the neural network to estimate this like tau I and tau H. Okay. So this is a direct effect. We're going to utilize just like ReLU neural network to estimate it. The point is that neural networks have kind of a universal approximation power. So even the treatment effect can be very complicated, depends on the individual's covariance, and it can still capture this complicated and nonlinear relation. And for the spillover effect, this is where we're introducing this like attention mechanism. Okay. So you have to consider two parts. So the Wij, this red part, this is the pairwise influence. You can imagine this is basically quantifying some similarity between xi and one of its neighbors, xj. Okay. And beyond that, we multiply by this like blue part, this alpha ij. So this is the adaptive attention weights. Okay. So this is actually exactly the architecture in the transformer when you utilize this attention weights. So it comes from this beta. This is called like a temperature parameter. So when the beta is 0, basically you assume the spillover is evenly across all the neighbors. And if the beta is very large, for example, if the beta goes to positive infinite, meaning that this individual I will only affected by the most influential neighbors, okay? Some like a k. The k has the largest similarity between I and the k. And the point is that you can estimate this temperature parameter beta from the data. Okay, you don't have to pre-design this one. And based on this like attention-based spillover mechanism, we can finally get our heterogeneous exposure mapping. Okay. So yeah, so of course, you know, then we have a lot of theoretical analysis and numerical analysis to demonstrate that we actually can utilize this attention-based spillover effect model to recover the signed relation, okay, positive and negative spillover effect, and of course get the, I think the most important, yeah, the influential neighborhood detection. We can actually detect who is the most important like neighbors, like for individual in the network. Okay, I think yeah, that's it. Yeah, thank you for the attention. Yeah.
Okay, thanks, Yubai. I think we have time for one or two questions.
Yeah, thanks. Very clear, nice presentation. Love it. I had one quick question. You glossed over sort of the second assumption of the network unconfoundedness as a standard assumption. And I'm just wondering from a more pragmatic standpoint for your assumption too, could you say a word about how realistic that is or isn't? I understand it's a common assumption, but I'm a little worried about it.
Yeah, I think that's a very good point. And this is actually something, if you want to refer, kind of get the causal effect just purely based on observational study. Okay? And this is the problem. The first thing is that, first thing you can do is that collect as many as covariates we have, because eventually this X will be input into like a transformer-based like attention. You do not need to worry about the dimension. Okay, this is different from the traditional statistical method. And the other thing is that also notice that we also allow the confiner exist within the network. In other words, if you condition a network, and most of the time, the unobserved confiner on the over the network can be captured by the topology structure of the network. For example, if you have the community structure, you can assume that the people from the same community, they have the same level of baseline outcome. Although you don't know the exact number of what's the unobserved confiner look like, but you can utilize the topology structure on network as another control of the potential unobserved confiner. And eventually, if you do not believe that you find all the confiners, you can still utilize the sensitivity analysis, saying that to what extent your conclusion gonna change, okay, based on the how many confiner you believe you do not capture. So I think we do have a lot of ways to analyze and to prevent the effect of the unobserved confiners. Yeah. Okay.
All right, one more quick question.
Thank you. Do you have assumption of temporal dependence here as well?
Yeah, I think that's a very good question. So as we mentioned, so in this framework, we only have one time single observation. We only have one snapshot on the network. And definitely this can be extend to the situation when you have a temporal network. You only have add one additional dimension time in the outcome model and all this like attention model. But I think that we have additional benefits because when you have the temporal structure, you have a different way to define spillover effect. You can utilize the treatment from the previous time points and how that will affect the next time point outcome. So typically people think that this have a stronger, it's maybe a stronger version of spillover effect from a causal perspective. I think that's additional gain, like beside the methodology building, yeah.
All right, thanks, Yubai.